Some of the notes that are provided on here you might want to highlight or underline as I'm talking through it. But it's basically, I'm gonna be referring to the video too, and in the amounts of the bailing beakers. Like, I would consider him like the product side and consider her the reactant side of the reversible reaction. Because in order to have equilibrium, you need to have reversible reactions. Okay? Okay. Now, a reversible reaction is eventually going to lead to that equal rate. As you saw, they were tossing the cups the cups of water back and forth until they got to the point where they were equal amounts going at equal rate back and forth. And you saw that her side definitely had less amount than his side. The product side would have had a greater amount in that particular case. Now, sometimes it's the other way around, where the reactant side will have the bigger portion, and the product side will have the less portion. And then eventually, in very rare cases, you could have it so that there are equal amounts on each side. Okay, that's a rare occasion, but it does happen sometimes, or it gets close to that. Okay, we call this reversible reaction where we end up with our equal rates, the equilibrium state. Okay, the reverse and forward reactions are going at equal rates. The concentration of the reactants and products are going to establish a ratio and remain constant. Okay, so we're going to use something called the equilibrium expression in order to figure out a mathematical way to represent this and figure out which side's going to be favored, or the position of the equilibrium is going to lie towards that side. Like in the video, equilibrium position would have lied towards his side because he had the greater amount. Okay? And we're going to be using the molarity concentrations in our equilibrium expression. So you have to have a concentration in order to have a molarity. You have to be able to have a concentration in order to have a molarity. If you are a pure substance, you're not going to be able to have a concentration. Okay? You have nothing dissolved in something else. You don't have an amount of particles per unit volume. Okay? Pure substances don't have concentration, so they will not find themselves in the equilibrium expression. But let's go ahead and look at the generic form of the equilibrium expression. Okay? You're going to have a reaction. And in this reaction here, we have the little a means the coefficient of substance A would be some kind of compound or element there. Reactant 1. We'll call A reactant 1. So the small a here means the coefficient of that particular reactant. The small b is the coefficient for B, the second reactant there. Over here on this side is C. C is going to be the first product. Okay, and that little c is going to be the coefficient, and the little d is going to be the coefficient for reactant D there. A product D, the second product on that side. So the second product will be D here. So our generic form of our expression looks like this. Basically, it's going to be the products over the reactants. However, we're going to take the concentration. When you have something in brackets like that, like C, that means the concentration of C, and that's going to be in molarity, or moles divided by liters. Okay? So when we have something in brackets, make sure you note that it means it's saying what the concentration of. Now you saw that in the acids and bases as well when we had the little brackets around H pluses, or the little brackets around the OH minuses. That means the concentration of hydrogen, the concentration of hydroxide. Okay? So you're going to take the products, and you're going to put their concentrations on the top, and you're going to raise them to the power of their coefficient. So the little c is going to become the exponent here. The little d here is going to become the exponent there. Okay? On the bottom goes the reactant. So reactant 1 is A. It's going to be raised to the little power. B raised to the small b, which would be the coefficient of that one. And it's always the products divided by the reactants. That's our ratio establishment here. Okay? Now, they have to be aqueous solutions, AQ, because AQ means it's dissolved in what?
Water.
Water. So that means it can have a concentration. Okay, it's a certain amount of particles in the volume. The other thing you can have in equilibrium expressions are going to be gases, because gases take up the space of their containers. So gases are going to have a certain amount of particles in a certain amount of volume. And if you have particles per volume, moles per volume, you can have a molarity. So gases have a molarity, aqueous solutions have a molarity. The ones that do not have molarities are going to be solids or liquids. So these guys, if there's a solid or a liquid in your reaction, you have to leave them out. They don't get to be part of the equilibrium expression. I know, they get ignored and left out. And you can, if you really want to, you can fill them in with ones. If you feel like you need to fill them in with ones as a placeholder, you're allowed to do that. Products are in the numerator, reactants are in the denominator. Coefficients become the exponents. It tells you right here. So all of this is written here for you to refer back to if you get confused. KEQ, we're going to calculate this amount using this expression. And we're going to plug in numbers for the concentrations. And when we get the KEQ value, there's a couple designations we have. If KEQ is greater than 1, it means the products are favored. That means that the one on the top, the numerator, is a bigger number anyways. So in that case, it's going to be like him, where he has more of the amount on his side. If KEQ is less than 1, okay, it's going to be favoring the reactants, or the equilibrium position will lie on the reactant side. And that means if that were the case where KEQ is less than 1, it'd be like her beaker was more full, and the equilibrium position was more towards her. Okay? So let's do a couple examples, and then I'll have you guys work together in your groups. So we have a reaction. Uh-huh.
So you're saying favoring the equilibrium is going back to the video, just to be clear. You're talking about the side that is more full is favored?
Correct, or the equilibrium position lies on that side.
Okay.
That's exactly right. So when we say that which one has the more amount is the side that is favored, or where the equilibrium position lies is towards that side. Yes?
Molar concentration for gases.
Molar concentration for gases. Once again, gases are really spread out particles, right? They fill the shape of their container, right? So if you put them in a closed container, they're going to spread out and fill and bounce off the walls of the container, right? So we can measure a concentration for a gas because we can count the number of particles in there in the certain amount of volume we've put it in. So gases can have a concentration. Okay? Whereas solids and liquids can't, because the particles are in a certain amount of volume, but if you take away some of the particles, you equally take away that same amount of volume, so your concentration never would change. Do you see what I'm saying? So that's why we leave out solids and liquids. Okay? So here, for equilibrium expression, if we're following the stuff on the front here, what's going to go on the top of the equation? The products. So I'm going to look over here. In this case, how many products do we have in this reaction?
One.
Only one. So there's only going to be one thing that goes on the top. Now we also need to check our physical states. Make sure that they're ones we're allowed to include. This one's AQ. Can we include it? Yes, it will have a concentration. It's dissolved in liquid. So we would put the concentration of NH3 up here. And what power should I raise it to? A2, good, like so. Now, looking at our reactants, because we only had one product. Our first reactant is the nitrogen. Are we allowed to include it?
Yes.
Yes, it's also AQ, so it does have a concentration, so we will include it. Good. Do we raise it to a power? We could put a 1, but anything to the 1 power is itself, correct? so we don't really need to put the 1. Okay? And last but not least, H2. On the bottom here, it's going to be H2 raised to the what? 3rd powered. We're going to cube that. Now, when I put two things next to each other like that, the N2 concentration times the H2 concentration cubed, what do we have to do with those when they're right next to each other? You're supposed to multiply them. Okay? When they don't put a little symbol between them and they give you those brackets, it means to multiply. Okay? And that would be the expression for this particular reaction. We call that the expression. There are no numbers. We just kind of show how it's represented. But if we look at the second part of this problem, guess what they're going to give us?
Numbers.
Some actual numbers. So the ammonia concentration is 0.933 moles per liter. So it's telling us at equilibrium, this is how much of the ammonia we got. Okay? That's after the equal rates have been established. Okay? So what I'm going to do now is plug and chug, substitute in my numbers. Okay? It's just like a formula now. We're going to substitute in the numbers. So on top, we're going to put in the 0.933, okay? And we need to raise it to the what power? The 2nd power. Good, like that. All right. Then on the bottom, for nitrogen, what did they tell us its amount is? 0.533, right? I don't really need to raise it to a power because remember that's a 1 there. Understood 1. Okay? Now, we need to do the hydrogen. What does they tell us the hydrogen's molarity is? 1.600, and we need to do what with that one? Cube it. All right. So, now this is where it gets a little more difficult. In our calculators, there is an x squared button, like that, near the log button at the top. Okay, there is also one that does this x to the y like that, and that one is like right above the C button. Okay, it's over to the right in the 3rd row down. We're going to be able to use these buttons to help us calculate. Okay, so I can do the top real easily. I can put in 0.933 and I can just do the square. 0.870489, right? Okay, so that's our top number. Now for the bottom number. Okay, what we need to do is we need to cube this guy first, probably. So if you type in 1.6, then you hit the x to the y button, and then you put the 3 in for the cube. There is? Oh yeah, just shift to the and then there's like the play or the triangle button. But yes. So if I put in here 1.6 and I do x to the y and then type a 3, it's going to cube it for me. But I still need to continue and multiply it by the other number on the bottom, 0.533. So what's the number that's going to go on the bottom?
2.183,160.
Okay, and I know this would be much easier doing the graphing calculators, but we're not going to be using them on the SOL. So we want to make sure that we're doing this correctly. So what did we get for our K value? 0.3987. How many sig figs should we keep? This one has 4. This guy has 3. This guy has 3. So we're multiplying and dividing, so we should keep 3. So 1, 2, 3. Do I round the 8 up or leave it alone? Round this up. Good. So we get. Now, this number, that's our KEQ number. What does the KEQ number now tell us about the reaction? Is it KEQ greater than 1 or less than 1?
Less.
So, how do I know? I know because KEQ is less than 1. That's this part of the question. So, are the products or the reactants favored in this one? Reactants are favored. Good. The equilibrium position lies on the reactant side. Okay? I know this because KEQ is less than 1. The denominator is a much bigger value, so when I do the division, my number is going to come out less than 1. Okay? So, would it be her beaker or his beaker that is more filled at this point? We're considering her the reactant, so yes, hers would be where the equilibrium position. Hers would be more filled. Okay? Yes?
So, my question is less than 1 is the reaction.
It would be the reactants. If KEQ was greater than 1, it's going to be the products. Now, let me throw one more thing at you. What happens if KEQ equal to 1? What does that mean?
It needs to both equal.
Well, everything's at equilibrium, because remember, equilibrium is just equal rates. What are we talking? Their amounts are now going to be the same. So the equilibrium position is equal amounts here. Okay? Doesn't lie on either side. They're equal. Okay? That's rare. Doesn't happen very often, but okay. A lot of times, a lot of reactions go heavily on the product side, and then some of them barely get started, so you have more reactants. Okay? So what I'd like you to do for the next 10-15 minutes is start the practice. Now, be cognizant of, say, like something number 2 here. Number 2, what do we need to consider first in writing our expression? Gases and the
Liquids, pure liquid.
What do we need to consider before we like number 2 might throw you for a loop, because what do we need to look for before we write out our expression? Any gas is an aqueous. So what do we want to ignore? Solids and liquids. So for this one, I'm just going to, because it has 2 solids in it, right? I'm not going to include those in my expression at all. They don't find a place. Okay? So don't forget to look for those physical states first, to make sure that you only put the AQs and the gases, the Gs, in the expression, right? So spend like 10-15 minutes going over that. I'm going to come finish checking around while you're doing that, and let us know if you've got questions. So let's check our answers and see if we plug things in right. But before you even try to plug numbers in, you need to write out your expression. If you don't write out your expression, you're not going to know how to do it. And it tells you first that you need to, using your equilibrium constant expression, okay, you need to determine that first. So for this one,
Remember to use concentration.
so there's our equilibrium expression. We just put the products on the top, which was only one product. Put the reactants on the bottom. They were all gases, so they all get included. Okay. Now we just substitute in our numbers. We're going to plug and chug. So our ammonia goes on the top. Oh, don't forget your sig figs here. They are significant. And we're going to square that one over. The first one on the bottom is 0.0200. Second one on the bottom, 0.0200. But this one is cubed, right? So if you plug that into your calculator right, you should have gotten 625. 625 seems like a huge number, but it's really not. Some of our K's can be like 1 times 10 to the 7th, like super huge. So K values, they vary based on the ratio of the products and the reactants. So this case, KEQ is greater than 1. So what does that mean about our equilibrium position? Which side? Product side. Good. Product side is where our equilibrium position is located, and it's favored. Now, what you should have noticed about number 2 is the only thing you get to include is the one product. So KEQ was going to be O2 cubed. Now you could put a 1 on the bottom if you like, if that you need a placeholder. That's okay. You can put the 1 in to make it make more sense to you if you like.
The good part of that is that you're showing us that you understand that the rule is, if it is a solid, then the concentration is 1. Showing us that you understand that rule.
Well, the concentration shouldn't be changing for the pure substances, so we don't include them, yes, and you can substitute into that particular part of the equation and hold it the place for a 1. If it was reversed, where it was only the reactant, you would put 1 over the reactant and then calculate it that way, okay? So keep that in mind. So here we're going to put 0.0500, and we're going to cube it. And what do you get out of that? 1.25 times 10 to the what? -4. Good. So is that KEQ greater than, less than, or equal to 1? Less than 1. So where does the equilibrium position lie? Reactant side. Whose beaker's more filled, hers or his? Well, which one is it? Hers or his? Hers. She was the reactant. She represented the reactant side. He represented the products in that Baling Beakers video. Now, I do want to make one correction before we move on to the Le Chatelier's principle. I love saying his name, by the way. We have found a typo here, so please correct it. The typo, because carbonate doesn't have a +2 charge. That's just ridiculous. This is carbonate. It should be a -2. So change that, please. And in that particular reaction for number 5, lithium carbonate as a solid, we put it in water. It's now going to break apart into its ions. So they're both AQ, so you would only include these guys. And also, just a quick little review, if it breaks apart into its ions like that, is it going to be able to conduct electricity? Is it an electrolyte? Yes, because it's going to form the ions. Now it's going to have charges, and now you can conduct electricity through it. So don't forget that ionic solids that dissolve in water and form their ions, they break apart, dissociate. They are going to be electrolytes. They like that light bulb question on the SOL, I'm just telling you. So we're coming back to that one, okay? So you do need to complete all 5 of these. So if you haven't already, I've seen a lot of people working hard and getting it done. So that's good. Doing a good job. But we do need to talk about Le Chatelier. And he's a French guy. Le Chatelier.
The French never pronounce the R's at the end.
Yes. The R is silent. Now, I do need your undivided attention, so please tune in here because there's a lot of different factors going on. A lot of different factors. You can have changes in concentration. Changes in concentration. Basically, I have a system at equilibrium. I have a reaction and it has its established ratio of products and reactants, has its own KEQ value, but I come in and I stress or change something in the reaction. I like remove one of the reactants, or I add pressure, or I change the temperature. I do something that changes the equilibrium. So what basically the reaction does when you do something like that is it basically tries to reestablish the equilibrium, and it has to shift in order to reestablish what it once had. So you stress the system some way, shape, or form, it's going to go back and try to reestablish equilibrium. Now, if you change concentrations, okay, you change concentrations, you can either do it 2 ways. You can add in more stuff, or you can take away stuff, remove stuff. If you add something into a reaction, it's going to shift the other direction, go to the other side. That's the first thing. If you remove something, it is going to believe that it's missing, so it's going to shift towards the side that you're removing it from. Does everybody understand that?
So when you move something, basically, the product will feel like something is moving. So shift to the side that you was moving.
the one that you remove from is the side it's going to shift towards. Okay, now let's look at a few examples. Okay, I'm going to have you look at this one in the chart. So we're going to do each different change one at a time. So here is our overall reaction. Okay, now we'll get to the kilocalories and why that's there in just a minute. But I have nitrogen plus hydrogen giving us ammonia. Now this is called the Haber process. It's a very important reaction. It makes ammonia that goes in fertilizer, and if you're a farmer, you need lots of fertilizer. So we need to be able to manufacture it and be able to produce our crops. So it's called the Haber process. That's why I keep using this one. It's a really good one that they use. They manipulate this equation very well to make sure they're making lots of ammonia. So if I add in hydrogen, I'm going to be adding it in here. And I just said if we add something in, it's going to shift to the other side. So which way am I going to shift? To the left or to the right? I'm going to go this way, right? So now, the other thing you have to consider, if I shift to the right, the things on the left are going to decrease. The things on the right are going to increase, right? So, shifting to the right, what happens to my N2? It decreases, okay? If I shift over here, what happens to my ammonia? It increases. Okay, I'm using arrows, but you can write the words in if you like to do the words. Hi.
He was wondering if you needed to, so if you're in the middle of the lesson, then.
Okay, so let's look at another example. Let's look at removing. If we were to remove N2, we're taking it out. Okay, so I'm taking this stuff and I'm removing it. So it's going to see, oh, N2's gone. I need to make more N2. So which way is it going to shift? Left. It's going to go this way because it needs to make more N2. So it'd be left. So if we're shifting towards the reactants, what happens to them? Are they going to increase or decrease?
Increase.
They should increase. So our hydrogen is going to increase because it's a reactant, right? Shifting this way increases reactants. Now the product, the ammonia, guess what's going to happen to it? It's going to decrease. Okay?
But how the reactants increase? Because the N2 is more.
Well, you're taking away the N2, so it's going to keep adding to that side. So they're going to go up. But that's why the N2 is crossed out, because we're not really looking at the N2, because we're already manipulating the N2. We're only caring about what's happening to the hydrogen and the ammonia at that point.
So
Okay?
it's like saying you can take with the N2 reactants. It's going to bring the N2 from products over, right?
No, it's going to start changing the ammonia into H2 and N2. Basically, it's going to start making the ammonia break down into hydrogen and nitrogen to replace the missing nitrogen. Does that make sense? So good question.
So whenever the element moves to left, the reaction will increase.
The reactants increase and the products will decrease. That's exactly right. All right, so one more. Let's look at if we remove the ammonia. Removing the ammonia, which way is it going to shift?
Left.
We're removing this out. So it's going to want to replace the ammonia that you're removing. So which way should it shift? To the right. Good. We're going to go to the right now. So if I'm going towards the products, who should increase? The ammonia. If I'm going towards the products, that means the reactants are both going to decrease. Okay? That is the first thing you can change, concentration. So let's talk about temperature. What happens when we change temperature? We need to look here at our reactions. Remember, we have exothermic and we have endothermic. If we have an exothermic reaction, we are releasing heat. Where does the heat belong? Is it a reactant or a product? See right here how they put it on the product side. Okay? It is a product. And we treat it just like anything else. If we add in temperature, you're adding in heat. You go the other direction. If you take away heat, you're removing heat. Or you're decreasing the temperature, you're removing heat. So you go towards the side that has the heat. Same idea, adding and removing. Still applies here. But now we're just looking at the heat only. So exothermic reactions have heat as a product. Endothermics have heat as a reactant, right? Now there's a couple different ways to represent this. They could give you a delta H value. Exothermic reaction, the delta H's are always going to be what? Positive or negative? Negative, good. Exothermic, remember, the products are lower than the reactants, so you're going to have a negative delta H for heat of reaction. How about here for the endothermic? Should be positive. As you can see, the product line is higher than the reactant line. So if you see a positive delta H, put the heat as a reactant. If you see a negative delta H, put the heat as a product. Actually, write it in there. That's what I do. Okay? So let's go back and look at our examples here for that. Oops, wrong way. Sorry, going the wrong way. All right, so increasing temperature. It tells me the kilocalories are right here. Kilocalories are a measure of heat. So what kind of reaction am I dealing with here? This is your heat. This is an exothermic, so the heat's at product this time. Okay? So if I increase the temperature, okay? Increase the temperature. I'm adding in heat. That's what I'm doing. I'm adding in here. I shift to which side? I go left because go the opposite way. Opposite way away from the heat. So that means the reactants will increase, the product will decrease. So if you add in heat, treat heat like it's just another part of the equation. You add it in, it goes the other way. So if I'm adding in something on the product side, I shift the other way. Go the other way. Yes. It goes towards the products, correct. Yes. Adding is opposite, removing is same. All right, if I decrease the temperature, I'm removing the heat. It's going to say, oh, my heat's disappearing. So what is it going to do? Make more heat. So which way should it shift? To the right. It's going to try to replace the heat that's gone. So now our reactants decrease and our products are going to increase. Because they're making more ammonia. They're making more of the products. So they're going to start getting used up because they're shifting to the right.
Oh, to make heat, they have to use the reaction.
Okay, now the pressure thing. The pressure only really is accounted for when we're working with gases, because gases are the only things that are going to exert pressure. Pressure is the bouncing off the walls of the container, right? So you have to look at the moles of the gas. So you need to, whenever you're looking at pressure, you need to add up the moles of the gas on each side of the equation. So let's look here. How many moles does this represent? A 1. And it's a G, so that's a gas. 3 moles, G, that's a gas. You only count it for gases, though. So on the reactant side, what is our total moles of gas? 4. On the product side, what's our total moles of gas? 2. We only have 2, yeah. Correct? So, this is how pressure works. To increase the pressure, it shifts to the side with the least number of moles.
Oh, so it goes to right.
If we increase the pressure, yes, it's going to go to the right. Good. If I go to the right, my reactants decrease, my products increase. Now, if I decrease the pressure, you can assume that reverse is true. I go to the side with more moles of gas. So if you decrease the pressure, it goes the other direction. So it would be less, correct. So our reactants will increase and our products will decrease. Now, the only other thing I can tell you about pressure, you got to pay attention to if they refer to a volume. Because pressure and volume are inversely related. So if pressure increases, what happens to your volume? It goes down. So what if they said we decrease the volume? Then you would say, oh, that means increases the pressure. And if they said we increase the volume, that would mean decrease the pressure. Because this is an inverse relationship. So if volume is increased, the pressure is going to decrease. So they are opposite each other. So if it refers to volume, realize, oh, they said the volume increases, pressure decreases. They say the volume decreased, the pressure increased. Okay? So I would like you to work on these. You have your people at your tables too to help. But they gave me a delta H here, so what should I do immediately? It's positive, so where do I put my heat? Stick it as a reactant, so you know where it goes. Automatically stick it in there. So you're like, oh, temperature increase, that's adding heat. Now I'm going to shift, okay? So you are responsible for finishing everything in the packet, but you can get a lot of this done, because all you really have to do is draw some arrows here, shift right, shift left, okay? So go ahead and do that. I'll be walking around, and you have some people at your table to help you. Do it here, do it now. Oh, I did forget one more important thing, just to let you know. This one has a what in it?
Oh, water.
Water that is a liquid. Liquids and solids do not affect equilibrium. So if you see them in here, okay, that is not going to affect equilibrium. So if they said increase water, decrease water, you would say no shift. Because the water, because it's a pure substance, does not affect equilibrium. The other thing I forgot to mention too is the catalyst. Catalysts, guess what they do? What do? You remember that? Speed up the reaction by lowering the activation energy. Catalysts, though, for equilibrium reactions, they speed it up in each direction. So there is no shift when you add a catalyst. No shift. Catalyst will speed up in both directions, so nothing changes when you add a catalyst. Forgot those 2 points there. Okay?